Hi everyone, how are you today? I hope you're all doing well. We've covered some concepts related to rotational dynamics. We'll use this to answer a real-world problem. Here's the problem: a ball rolls down a 60-degree inclined surface. The question is, what is the acceleration of the ball? Wow, this problem only contains one quantity, the angle of inclination. Can we answer this? Let's show you a visual example. Here's an inclined surface. An inclined surface is actually a flat surface that is not parallel to the horizontal axis, but forms an angle to the horizontal axis. So, the trajectory is still a straight line. On that surface is a ball. We're using colored balls to clearly see the changes in points on the ball's surface. The ball is rolling. This means that while it's moving translationally, it's also rotating about its own axis. From this, we understand the motion of the ball. Now, we'll identify several quantities related to the ball. Remember, we're free to choose a reference. The reference is chosen to simplify the calculation process. The choice of reference will not change the outcome of the process, it's just a method. Let's assume the ball's trajectory is the x-axis. And the line perpendicular to the x-axis is the y-axis. The center of the coordinate system is the center of the ball itself. Next, we'll analyze several forces acting on the ball. The ball is on the Earth's surface. It experiences a downward gravitational force. The ball doesn't penetrate the surface of the wood. This means that the ball experiences a normal force perpendicular to the surface of the wood. Both of these forces act at the object's center of mass. They don't cause the ball to rotate. The only force that causes the ball to rotate is friction. Because this force has a moment arm. Without friction, the ball would slide on an inclined plane, not roll. See, none of the forces are in a straight line. We need to arrange them so they're all in a straight line. Remember the component vector? Yes, we can decompose that vector into several vectors without changing the original vector. We can decompose the gravitational force vector into a force parallel to the direction of motion and a force perpendicular to the direction of motion. It seems all the forces are now on their respective axes. Now we can begin to analyze the translational motion of the ball. The ball only moves along the x-axis, meaning the resultant force on the y-axis is 0. Mathematically, sigma Fy equals 0. N minus W cosine beta equals 0. This is equation 1. On the other axis, sigma Fx equals max. There's a subscript x to indicate that this is the acceleration along the x-axis. Since the acceleration along the y-axis is 0, the magnitude of the ball's acceleration is simply the acceleration along the x-axis. The magnitude of a is equal to ax. We can write the right-hand side as ma. W sine beta minus Fk equals ma. Let's call this equation 2. Next, we will analyze the rotational motion of the ball. Sigma tau equals I alpha. This is the form of Newton's law for rotating objects. We are already familiar with this from the previous series. As mentioned, the force causing the ball to rotate is simply Fk. The moment arm of that force is r. Fkr equals I alpha. The moment of inertia is 2 over 5 mr squared. In rolling motion, alpha equals A over r. Review the rotational kinematics course to understand this in more detail. This equation can be simplified as Fk equals 2 over 5 ma. We can manipulate some of these equations to find the acceleration of the ball. The easiest way is to substitute equation 3 into equation 2. The gravitational force is mg. We can simplify this equation to 7 over 5 A equals g sine beta. Or, A is equal to 5 over 7 g sine beta. It turns out that the acceleration of an object depends only on the geometry of the space. The value of beta is 60 degrees, and g is 10 meters per second squared. A is approximately 6.2 meters per second squared. Hope this is helpful. And don't forget to watch the next video.